All right, this video is going to be a pretty brief overview of slope stability, just to define a few terms and maybe most importantly define our definition of the factor of safety. So here's a little sketch of a slope that involves a deep-seated failure. So that means that the failure surface would be somewhat deep below the ground, and you would have this kind of in this case downward and leftward movement of the slope mass. So the toe of the slope is here at the bottom. The head of the slope is up here, right, or the crown. And then after a slope has failed, you'll see a headscarp. So that's where there's a geomorphic rise or a topographic relief here. What happens immediately after a slope failure is really easy to see these headscarps. After some time, vegetation grows there and it can be a little bit more challenging. Good geologist can identify these from aerial photos or topographic maps or features or just being on site. So this blue line is kind of the deformed shape of what would happen. And the slope is held in place by shear stresses acting along this potential failure surface, and it fails when the shear stress is equal to the shear strength, and then the slope moves. Slopes can also have these sort of superficial failures. That's where a very shallow zone of soil kind of ravels downhill. And you've probably experienced that kind of slope failure before if you've ever dug a hole in the sand at the beach. Dry sand will have this kind of superficial raveling failure where you just see particles kind of rolling downhill. The factor of safety for these two might be the same, but the superficial failure likely has far less impact, right? If you have buried utilities or a house up here or something like that, the mass of soil moving is much bigger for a deep-seated failure. Of course, both could have adverse consequences, so we need to worry about both kinds. Okay, let's move on to our definition of factor of safety. I think we all have a general idea of what the factor of safety means, but in slope stability it has a very specific definition that we need to follow. The factor of safety is equal to the shear strength divided by the equilibrium shear stress. So here S is shear strength, tau is equilibrium shear stress. That's different than the factor of safety you might get from a foundation problem, which would be the amount of vertical pressure you can apply to the ground surface divided by the amount of pressure that would be required for that bearing failure to happen. So it's a little bit different in terms of these definitions. We often rearrange this. So this expression right here is the factor of safety. A lot of the time we rearrange it and put the equilibrium shear stress is equal to shear strength divided by factor of safety. And you'll see why we do that when we get to methods of slices. And then if you plug in the Mohr-Coulomb failure criterion up here, you get this equation. Tau is equal to C plus sigma tangent of phi divided by the factor of safety. And we assume the factor of safety is constant for a particular slope problem, although the strength and the equilibrium shear stress may vary spatially along the length of the slope. You can imagine the strength up here might be a lot lower than the strength down here. So anyway, the factor of safety we're assuming to be the same everywhere within the slope. Then there are three primary methods of analysis of slope stability. The first one involves single free body diagrams, and that's what we'll study first. These would be things like infinite slope analysis, the log spiral method, the Swedish circle method. That's where we just divide the slope into a single free body. Like for example, we would analyze this shape as being a free body diagram, and we would figure out the factor of safety based on the shear stresses acting on that surface relative to the strength. And of course then there's also the weight of that sliding mass that will cause it to tend to rotate, in this case rotate clockwise. So a lot of the time we're using moment equilibrium, sometimes force equilibrium to solve these single free body methods. And it means that the geometry has to be fairly simple, right? The geometry and the strength both have to be fairly simple in order to get away with doing this. Okay, the most common method for analyzing slope stability are the methods of slices. And this involves multiple free body diagrams So a lot of the time the geometry or the strength are complicated, and we have to cut the free body diagram into multiple, typically vertical slices, and make assumptions about how those slices interact with each other in order to render the problem statically determinate so we can get a solution. There are a lot of different assumptions we can make about how the slices interact with each other. Therefore, there are a lot of different procedures of slices because they all make different assumptions. So there's the ordinary method of slices, kind of like the first method that was developed. Then there's the simplified Bishop procedure. Then Spencer's method and Morgenstern and Price. A lot of these methods like these were formed in the 60s and early 70s. There haven't been too many new methods of slices since then, so not a huge advancement in our understanding of limit equilibrium methods using method of slices since that time frame. Of course, there are others, a lot of other methods too. This is not an exhaustive list. One thing I'll point out here that we'll visit again later, for a two-dimensional slope stability problem, which is what we tend to solve because it fits neatly onto a single plane, we can analyze it easily. There are three equilibrium conditions. If we have this coordinate system, x, y, and z, you would have the sum of forces in the x direction have to be equal, sum of forces in the y direction have to be equal, and then the sum of moments about the z-axis, or the rotational moment in the plane, has to be equal to 0. One thing you'll find is that not all of these methods satisfy all three equilibrium conditions. In particular, the ordinary method of slices and the Bishop simplified procedure do not satisfy all three equilibrium conditions. So you end up with a solution for factor of safety that's not even in static equilibrium. As a result, you really shouldn't use those methods. They're kind of relics of the past. Now with modern computing power, there's no reason for us to use the ordinary method of slices or the simplified Bishop procedure, maybe outside of a classroom setting where we're trying to study these methods and learn what their assumptions are. Okay, then the last method is the strength reduction method. One of the problems with limit equilibrium methods is that in order to divide the slope into a whole bunch of vertical slices, you have to assume that there's a failure surface. So first, maybe we draw a circle and say this slope is going to fail along this circular arc. Then we can divide it geometrically into vertical slices, make assumptions about how those slices interact, and solve for the factor of safety. We don't know if that circle is the critical one that's going to cause the lowest factor of safety to come out of our calculation. So we would then try another circle, maybe like that, and then another one like this, and we repeat that process thousands of times typically to find the one that gives the lowest factor of safety. So the factor of safety we compute that way is actually a lower bound, right? It's an upper bound. It means the factor of safety is equal to or less than the number that we've computed using limit equilibrium. If we don't do a good job testing the right failure surface, we might get the wrong factor of safety and we'll be unconservative. We'll overestimate it. Okay, the strength reduction method does not require us to assign a predefined failure surface so that we can do our analysis. The way that this works instead is you set up a continuum analysis, like a finite element or finite difference simulation. And of course, an output of those simulations is just stress fields and deformations and strains, not factor of safety. So what you have to do is reduce the strength systematically and solve for the displacements each time using an elastoplastic solver. And then when the deformations become too large or larger than a specified threshold, you assume that the soil is now failing and you've computed the equilibrium shear stress that way, right? So the strength reduction factor, the amount by which you have to reduce the strength, is equal to the factor of safety when you reach that condition of having too much deformation. Huge benefit. There's no need to pre-identify the failure surface. So if you have a complicated failure mechanism, strength reduction method might be really good. The downside is that it takes a little bit longer to run and it requires a little bit more expertise, but it is a really nice method. And we'll use all of these methods in this class.